Today, I want to talk about one problem that's easy to miss. When we say DFE, most people think about data DFE. Data DFE is used to open the data I at the center of the UI. But in a CDR-based receiver, the data sampler is not the only important sampler. We also have the edge sampler. The edge sampler looks at the transition point. That transition information is used by the CDR to decide where the recovery clock should be. So the key idea is this. If the data I is clean, but the edge crossing is still dirty, the recovery clock can still be noisy. And once the recovery clock is noisy, you'll come back and hear the data sampling point. So data DFE only solves half of the problem. Edge DFE solves the other half. Data DFE clean the I. Edge DFE clean the clock information. A normal data DFE only cancels ISI at the data sampling point. The point is near the center of the I. But the CDR does not recover the clock from the center of the I. The CDR recovers the clock from the edge crossing. So if the edge crossing still has ISI, two bad things happen. First, the I near the crossing is curved. If the sampling clock is not exactly ideal, the data sample may move to a weaker part of the I. That means less voltage margin. Second, ISI can move the edge crossing earlier or later. This creates data-dependent jitter. The CDR sees this shifted edge and may look to a noisy phase. Then the recovery clock carries this noise back into the data sampler. So the problem becomes a loop. The edge creates bad clock. Bad clock creates worse data sampling. This is why data DFE alone still can fail, even if the data I looks improved. A natural question is this. If edge jitter is the problem, can we just make the CDR bandwidth smaller? Maybe the CDR can average out the edge noise, but the paper shows this is not enough. The edge ISI noise has a very wide spectrum. It's almost like white noise. That means the noise is spread across the frequency. A narrow CDR can remove some high-frequency noise, but it cannot remove everything. Also, we cannot make the CDR bandwidth too small. The CDR still needs to track dual input jitter. You also need to meet the JTAL requirement. So, the CDR bandwidth is constrained. We cannot just slow it down forever. The paper gives a very important example. If edge jitter increases from 0.1 UI peak-to-peak to 0.15 UI peak-to-peak, the array can degrade from 1e-12 to 1e-11. This is only a small timing change, but it caused 1 decade of bit array degradation. So the message is simple. CDR bandwidth control alone is not enough. We need to reduce the edge ISI before it enters the CDR. Before using Edge DFE, we may think about 3 simple fixes. The first idea is more CTOE boost. This can make the waveform sharper, but CTOE is a linear filter. It boosts signal and noise together, so high-frequency noise, crosstalk, and reflection can also be amplified. We may reduce deterministic ISI, but we may increase random noise, so bit array can still fail, just for different reasons. The second idea is edge-only equalization. This means we clean only the edge samples, but if we ignore the data path, the data sample can see more ISI, so the CDR may look cleaner, but the data bit array can become worse. The third idea is the transition filtering. This means we throw away some back transition before the CDR uses them. This can reduce some edge ISI patterns, but it also removes useful phase information. The transition density becomes smaller, then the effective CDR bandwidth becomes smaller, and jitter can become worse. So each simple fix breaks something else. More CTOE boosts noise. Edge-only equalization hurts the data path. Transition filtering removes timing information. That is why we need a better architecture. We need clean data, clean edge, and enough CDR bandwidth at the same time. The paper compares two receiver DFE architectures. Type 1 uses 1/2 symbol space DFE to equalize both data and edge. This sounds simple, but it creates a trade-off. The best tap setting for the data sample is not always the best setting tap for the edge sample. So if we force one equalizer to do both jobs, we may lose data AI high. This is similar to the TX-XFIR trade-off. We improve timing margin, but we can pay voltage margin. Type 2 is the better idea for the receiver. It uses two separate paths. One path is XDFE. This is a normal data DFE. It's optimized for the data sample and voltage margin. The other path is XEDFE. This is the Edge DFE. It's optimized for the edge sample and CDR timing information. Now, the data sampler and edge sampler do not need to share the same compromise. The data path keeps its voltage margin. The edge path gives clean timing information to the CDR. This is the main reason Type 2 XDFE is so powerful. It decouples voltage margin and timing margin. Instead of one equalizer trying to satisfy two masters, we now have two equalizers for two different jobs. But now, we have a new problem. If we add an Edge DFE, how do we adapt its tap values? A normal LMS algorithm may not converge. The paper shows that the coefficients can diverge. This happens because the edge equalizer and the CDR phase are coupled together. The loop has too much freedom. It can reduce the edge error by changing the edge DFE tabs, but it can also reduce the edge error by moving the CDR clock phase. So the adaptation does not have a unique answer. It may keep moving and never settle. The paper's solution is to add one constraint. They choose one reference edge. This reference edge is fixed. Then the other edges are adapted toward this reference edge. In this information implementation, this creates the hard constraint. Gamma 1 equals minus gamma 2 plus gamma 3. In simple words, we remove 1 degree of freedom. Now, the clock phase cannot freeze. The LMS has a stable reference, so the Edge DFE tab can converge. The simple explanation is this. Without an anchor, LMS can treat by moving the clock. With an anchor, LMS must really equalize the edge. That is why the modified LMS works. Alright, this measurement is the proof. The paper measured a 3.6 gigabit per second link. The transmitter was in a 0.13 micron CMOS. The receiver was in a 0.18 micron CMOS. The hardest channel was 120 inches of FIR4. That channel had about 24 dB loss at 9 GHz frequency. For this channel, the baseline case failed. With no equalization into the CDR does not lock. With a conventional data DFE, the application still fails. There is no stable lock point. But with the Type 2 XDFE and modified LMS, the receiver converges. The CDR locks near the optimal sampling point, and the major bit error rate is below 1E-14. The jitter improvement may look small. Recovery clock jitter improves from 31.1 picosecond peak to peak to 28.9 picosecond peak to peak. Edge ISI and total jitter are also reduced, but the system level result is very large. The link changes from no lock to error-free operation. That is the most important message. Edge DFE is not just a small waveform cleanup. It can decide whether a receiver locks or fails. Here are the summarized images showing you why we need Edge DFE, not just data DFE. Actually, data DFE and Edge DFE solve different problems. Data DFE opens data I. Edge DFE cleans the transition information used by the CDR. If we only clean the data I, but leave the edge crossing dirty, the recovery clock still be noisy, and the noisy clock can hurt the data I again. The Type 2 XDFE architecture is important because it separates two jobs. The data path keeps its voltage margin. The edge path improves the timing margin by giving cleaner information to the CDR. But Edge DFE also creates an adaptation problem. A normal LMS can diverge because the edge tabs and the CDR phase has too much freedom. So the paper used a modified LMS with one fixed reference edge. That anchor makes the adaptation converge. The major result is very clear. Across a 120-inch FR4 channel with a 24 dB loss, no equation does not lock. Conventional DFE fails adaptation. Only Type 2 XDFE with a modified LMS reach error-free operation. For modern high-speed links, the 56 gig and 112 gig timing margin is much smaller. So this idea becomes even more important. The final takeaway is simple. Data DFE fixes the I. Edge DFE fixes the clock. For a high-loss serial link, we need to think about both. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video with the people who may be benefiting.